Okay, so let's look at the parameterization of curves, because there will be times when we need to do a line integral, but we are not told what the parametric equation for a curve is. And the first statement I want to make is that there are absolutely infinite ways in which to do this. For example, if I look at this parabola, y equals x squared plus 1, and that is a parabola. Let's see, when x is 0, y is 1. When x is 1 or negative 1, y is 2, and so on and so forth. So here is our parabola. Well, just to give you an example of the number of ways to do this, let's suppose I let x be equal to t and y be equal to t squared plus 1. Then if I eliminate the parameter in this, I promise you I will get that equation. How do we eliminate the parameter? Remember, we solve each of these equations for t, so x equal t is already done. Here I'm going to bring the 1 over to the other side and then take the square root of both sides. So I get t is equal to the square root of y minus 1. And if both of those are equal to t, then they must be equal to each other. So we get x is equal to the square root of y minus 1. Going ahead and squaring both sides. X squared is equal to y minus 1. Or x squared plus 1 is equal to y. So that's one way I could do it. I could also come in here and let x equal to 2t and y equal to 4t squared plus 1. If I were to do that, eliminate the parameter, x over 2 is equal to t, and y minus 1 is equal to 4t squared. We can divide through by 4, then take the square root of both sides. So I get the square root of y minus 1 over 4 is equal to t, and then setting them equal, x over 2 is equal to the square root of y minus 1 over 4, square both sides. X squared over 4 is equal to y minus 1 over 4. Multiply both sides by 4. And I get that x squared is equal to y minus 1. And again, x squared plus 1 is equal to y. So we can see that there are just an infinite number of ways to do that. So what we're going to do here is we're going to try to standardize at least 2 of these, and these will be the ones that we're going to use. And again, the reason for this is that sometimes we'll need to do a line integral and we won't be given the curve in a parametric form, which means we'll have to parameterize the curve itself. So the first example we're going to look at are circles. Circles take on the form in general, standard form of a circle is x minus a squared plus y minus b squared is equal to r squared, where the center is located at AB and the radius is equal to r. And if we go ahead and look at our substitutions that we use to convert this over to polar by letting x equal to r cosine of t and y being equal to r sine of t, and then solving this, we will get that at least one good parameterization for this would be to let r of t be equal to a plus r cosine of t times the unit vector I plus b plus r sine of t times the unit vector j, where again the center of that circle is located at AB and r is the radius. So for our first example here, let's suppose I was asked to evaluate a line integral over this circle in the first quadrant. So I'm given the path here, but it's not parameterized. In order to do that, I'm just going to use this form here where the center is located at the ordered pair AB, which in this case would be 1, 0, and the radius is the square root of 4, which is 2. So the r of t would be equal to a, which is 1 plus 2 cosine of t times the unit vector I, plus b, which is 0, plus 2 sine of t times the unit vector j. And then the bounds on t are going to just strictly depend on what portion of that circle we're dealing with. We are dealing with just the portion in the first quadrant. So here t is going to sit between 0 and pi over 2. Very simple way to parameterize circles. The other thing that we're going to look at parameterizing are lines. And so I've given you some forms for doing it here. when we are given the curve or a line segment, that is a line segment, excuse me, from a given point P to a given point Q, what we're going to do is we're going to determine this direction vector and then go back to using the parametric equations for lines, x equal x naught plus at, y equals y naught plus bt, and z equals z naught plus ct. And again, in case you've forgotten, back in Cal 2, or Cal 3 actually, I guess, was the first time we looked at this, and we said that in order to write the equation of a line, there were two things we needed. We needed a point that the line passed through. So let's suppose that's my line, and P is a point I know. We would also need then any other point on the line, Q. And we would need something to indicate direction. Now in R2, that's simply a slope, but in R3, what we use is a direction vector, and that direction vector has components A, B, and C. If P is a point I know, let's call it x naught, y naught, and z naught, and Q was any other point on the line, x, y, and z, then there would be only one way to write a line that passed through P that was parallel to the vector V. And when two lines are parallel, they're scalar multiples. So we took the vector PQ and wrote it as a scalar, and in this case we use the scalar T times the vector V. And of course, to define PQ, it's just terminal minus initial in each case. So that's x minus x naught, y minus y naught, and z minus z naught, and that's going to be equal to t times the vector having components a, b, and c. And then setting those like terms equal, we got x minus x naught is equal to at, y minus y naught is equal to bt, and z minus z naught is equal to ct, because in order for two vectors to be equal, their components must be equal. And then solving this for x, y, and z accordingly, we got the parametric equations for a line in R3. That is, x is equal to x naught plus at, y is equal to y naught plus bt, and z was equal to z naught plus ct. So that's the basis for what we're going to use here to parameterize our line. In this case, we are going to know the beginning point and the ending point. So what we're going to need here is a direction vector. That is a vector that is parallel to our line. And a vector that is parallel to the line would just be the vector PQ, the scalar component, which would be a 1. So we're going to find our direction vector by looking at PQ. And then we're just going to use those definitions here, x naught plus at, y naught plus bt, z naught plus ct, where x naught, y naught, and z naught are the initial points that the line passes through, and a, b, and c are the components of our direction vector. And for each of these lines, and it really doesn't matter how many you have to do in a problem, we will always just set the value of t to be between 0 and 1. So even if we have to break a line down into several segments, each segment will have different values for our r of t, but it'll have the same bounds on each and every one. So let's look at an example here. Let's do the line segment from the point 1, 2, 3 to the point 0, negative 1, 1. So we'll call this P, we'll call this Q. This is important here. This is our x naught, y naught, and z naught. So there are two things that we're going to need. We need the initial point, which we have, and we need that direction vector. And for the direction vector, we're just going to use the vector PQ. And so you remember how this works. It's going to be terminal minus initial in each case. So 0 minus 1 is negative 1. Negative 1 minus 2 is negative 3, and 1 minus 3 is a negative 2. And this is where we get our A, B, and C. So our R of t then is going to be equal to x naught, which is 1, minus at, which is just 1t, times the unit vector I. And then we'll do y naught plus bt, so that's 2 minus 3t, times the unit vector j. And then finally z naught plus ct, which is going to be 3 minus 2t times the unit vector k. And again, for all line segments, no matter how many you do, even if they're in the same problem, we're always going to let range between 0 and 1.